Tom here from Lawrence Systems, and today I'm joined once again by Allan Jude from Klara Systems, one of the leading experts in ZFS development and implementation. If you haven't seen our previous interview, we dug deep into real-world ZFS mistakes, lessons learned, and future plans. I'll link that video in the description below so you can check it out. But in this video, we're shifting focus to something many have asked about, and that's NVMe performance and ZFS. This is a deep dive into where ZFS is and where ZFS is going. So let's get started on this topic of how does NVMe and ZFS really line up and where do they not line up?
Yeah, there's quite a bit to it. Like thinking back to, ZFS was originally created in the year 2001, so it's going to be 25 years old next year.
Wow.
It's getting up there. And so, at that time, hard drives were all that we had. And I think if my memory is correct, there were about 100 gigabytes was big for a hard drive back then.
I feel smaller, but yeah,
Probably
maybe
even
some
smaller.
enterprise stuff is there.
Yeah, you're right. Maybe even smaller. It was probably more the 2005 era when ZFS became open source that the hard drives were in the 100 to 200 gigabyte range.
Yeah, we were starting to
Yeah,
ramp up, but it
yeah,
is hard to grasp. I was thinking about this the other day that we can now download things far faster than the hard drives of that era can even write them. Like even the average internet connection is faster than an old hard drive can write speed. Things like
yes.
the times have changed greatly over the last 25 years when it comes to storage.
Yeah. A lot of the things you might download are bigger than an entire hard drive was back then.
Oh yeah. I updated the editing tool I use, DaVinci, and it's far bigger than the hard drive I had in the 90s.
Yeah. But yeah, so ZFS was designed back when there were just hard drives, and it did a lot of things to try to take advantage of the hard drive. So there are some limitations what hard drives can do, right? Because it's literally some spinning media and some actual physical actuators that are going to move around, it can only do so many operations per second because, if you're trying to read this sector and then you want to read a different sector, you have to physically move the head to the right spot and line up with the track and then wait for that sector on the platter to come around under the head again. And so that, with modern hard drives, that averages to about 4 milliseconds it takes to reposition and wait for the data to come around. So that means sometimes it'll be even slower than that, but the average is about 4 milliseconds. And so that means the most you can get is 200 to 250 operations per second. And also, we know that hard drives, kind of because of that, aren't good at trying to read and write at the same time because you're usually going to be doing that in two different places. And so you're going to make the head fidget back and forth. And so one of the first things ZFS does is try to spend most of its time reading and batches up all the writes that you're trying to do. And then once every 5 seconds, try to do all those writes at once while it holds off on the reads so that we can make the most out of the time we have with the hard drive. So that we can do as many reads as we can. And then when it comes time to write, we're going to write one big linear bit of data. So we're going to write it in one stream so the hard drive head doesn't have to move a whole bunch of times. So we're going to try to write it all out as quickly as possible and then go back to reading.
And being a copy on write file system, that batching just makes sense. You're going to get one contiguous spot on the drive, which is going to be better to read later. It's all about designing software to align with the limitations of the hardware of the day.
Exactly. And, to your point, it's also why fragmentation. So when we talk about fragmentation in ZFS, it's less the old kind you think about with like NTFS or FAT32, where your file might be broken up into a bunch of different places. In ZFS, the fragmentation we worry about is what's called free space fragmentation, where because we try to write all the data in one big block, it means if, when you delete stuff, you're only deleting, 1/10 of what you write most of the time. You can end up with all these little holes poked in the available space and not any one large contiguous bit of space, so that once the pool is full, when you're trying to write to it, finding a place where you can write all of the next 5 seconds of data in one place will be difficult. And if you have to start breaking that up, then ZFS is seeking again, and then the performance goes down.
Which is also kind of why you want to keep the ZFS system not quite full.
Yeah. So it is not like it was 10 or so years ago where, you could easily get to the point where you'd overfill it and things would break, or just when it got close to full and it would go so slow you couldn't fill it. It's not that bad anymore.
Curved down until you couldn't write data.
Yeah. There's been a lot of improvements, especially recently. Klara did a bunch of work to reduce what are called gang blocks. So if ZFS does have to, patch 3 or 4 different chunks of space together to make one space that's big enough, it creates what's called a gang block that basically says we're making one virtual block out of a bunch of these smaller blocks. So ZFS only has to address it once. Uh, but those were designed back when hard drives had a sector size of 512 bytes. But almost all drives nowadays have a sector size of 4 kilobytes. And that means the room we have for the header is now bigger. And so we can fit uh, more pieces in one of these gang blocks instead of having to have a gang of gang blocks. Because it was only 512 bytes before, we couldn't fit very many pieces to the tree. So we'd have to make this deeper and deeper tree. And it would get really cumbersome, and it would, because we'd have to seek and read over here to find out where to seek and read the next 3 pieces, it could really hurt performance. And so this recent change improves that. But again, it's another thing that when ZFS was designed, 512 bytes was what the sector size was always going to be. And that held true for, 20 years of ZFS, but then it suddenly wasn't true anymore.
Yeah, and that's what's
And
interesting is like how it's changed. It's also strange because I think, well, and you're probably gonna get more into this, how we address things in the logical block addressing. We're kind of imitating things now with hardware to try to keep some level of backwards compatibility over these 25-year life cycle we're talking about.
yeah, it's like almost everything we do on the computer now is still based on the same concepts of the way CPU works and the way memory works. We're basically, even though we're using these modern computers, they're all pretending from the programmer side to be an old like VAX PDP-11, which was, a one-core machine with like kilobytes or maybe a single-digit number of megabytes of memory. And so the fact that we still program in that paradigm, and then suddenly we have machines with 256 cores or threads executing all these things in parallel, and you're running more applications than there existed at the time back when these kind of concepts were come up with. And we have the same thing with hard drives, right? We have these logical block addresses, which is basically a sector number, and we just say the hard drive's laid out from beginning to end as this one linear list of addresses, and each one is a sector size and you can access it. But when we think about modern storage devices, specifically like SSDs and NVMe's, they have a controller with a component called a flash translation layer that keeps a map of that logical block address where the file system says it stored your file, and then where the SSD actually put it, because the SSD wants to be able to pick up that block and move it somewhere else, partly for garbage collection. In the NAND flash itself, you can't actually overwrite or replace individual sectors. You generally have to have a bigger chunk called an erase block. And so if that's 16 megabytes or 256 megabytes or something, it almost works somewhat analogous to the SMR drives for hard drives, where you kind of have to pick up all that data, put it somewhere else, erase the whole block, and start writing new data. The difference is the NVMe is usually under provisioned and has room to go put it somewhere else and change the mapping via this flash translation layer, instead of having to pick up all the blocks, erase it, and then put the blocks back where they were and fill in the holes.
Yeah, it is. I think SMR is a good example because I mean we know the challenges that has with regular spinning drives, but it's kind of a very similar problem. Like you said, if we have these larger blocks, we have to pick them up, move them, and that has a cost. And there's the alignment ZFS needs to have with that to make that more efficient, because it's better if you're writing. If there's a commit with more blocks, it'd be better to commit that with that larger size in mind for better performance.
Yeah, and the other thing that's difficult with tuning in ZFS or just in general is what is the best thing to do changes based on the device. So with hard drives, the bigger the chunks we can send it, the better. It's going to get more of this throughput because it's actually constrained just by the IOPS. But with actual like SATA or SAS SSDs, so not NVMe devices, but SSDs that are actually speaking the same old protocol as hard drives, if we send too big a chunks, it can actually increase their latency. Especially because they might have to do a garbage collection, right? You're trying to write this big chunk, and they can have that kind of same free space fragmentation problem that ZFS had. And so they're going to use the information they got from you running the trim commands to tell it which sectors aren't actually in use. and then rearrange a bunch of the blocks to make a big place for you to write to next. And so if you write to an SSD for too fast for too long, it'll actually have a pause or a stall while it goes and rearranges some blocks to make a next place for you to write. And so in ZFS, we aggregate the writes before we send them down to disk. So, even though you wrote a bunch of 4 kilobyte files or something, ZFS will look as like, well, if I arrange these right, can I make one big 1 megabyte block out of this that I can send to the drive as one command, and the drive will be able to then write that all linearly or stream it, and you'll get much better performance. But with an SSD in ZFS, we currently cap that to 128K, because if we give it too many blocks that are too big, it'll stall and it might not service the read that we send it next as quickly as we would like. So we'd like to kind of break those up so that other people can get in line at the same time. It kind of reminds me of being in line for a ride at the amusement park or something. If the line's really long and somebody with the golden ticket or whatever comes up, then they're stuck at the end of a long line. But if they kind of have two different lines, you can say, all right, we're going to take people from the priority line and fill up the line with people from the other line. But this way, if a high priority thing comes up, they're not at the back of hundreds of people. And so ZFS is doing that same thing to make sure that, if it's doing like prefetch, right? If you're reading a file, it can predict what block you might need next. And it will actually go and try to read that ahead of time, so that when you go and ask for it after, it's already in RAM and we get the ludicrous speed. But if at the same time a user's asking for a different block of data, like a second program running on the computer is asking for different data, we need to be able to get that done first and prioritize it over guessing what you might need next.
Yeah.
And so ZFS is spending a bunch of time kind of managing this queue and deciding when to send it down to the drive to keep the line short. So if something high priority comes up, it's not at the back of a long line. But with NVMe drives, the latencies are so short, the line runs so fast that if you don't keep it full, then the line is empty and the drive's sitting there twiddling its thumbs, waiting for you to tell it something to do.
Yeah, this is that concept that when you present that I found really interesting is the cycles of CPU you can spend looking for what that next predictive prefetch is are better. So just go ask, go get it type thing. The NVMe is so much faster. It becomes where the misalignment is and where the opportunity for optimization. This is not saying it doesn't work with NVMe. Just NVMe is outrunning the logic of ZFS as it stands today.
Yeah. So when we're looking at that aggregation, because it was going to take 4 milliseconds on average for each command, the CPU had lots of time to be like, oh, I'll just wait another 1 millisecond and see if any more things come in that I can group into one bigger thing. Whereas with NVMe, where it's going to take microseconds, if you had to tell the CPU, well, go to sleep and wake me up again in a second, or even in a very small amount of time, that amount of time, the NVMe could have done 10 things. And so with NVMe, it can be more advantageous to just send all of the things, including as small pieces, even if they happen to line up with each other, and just flood it down to the device, because it's going to finish them so fast that any time you spent trying to organize it and sort it would have actually just made it slower, not faster. But we have to not take out the feature, because it's still very, very important for hard drives. It does give you a lot better performance if you do sort it first.
Yeah, it's those things where the hardware's starting to outpace, and we are, ZFS has been around, as we stated, a long time, and that doesn't mean we need to rewrite a new file system, but we do need to enhance ZFS, I guess would be the status where we're at. So it's not that it doesn't work with NVMe's, like we kind of said in the beginning. It does work. It's still faster, but boy, there's potential here.
Exactly. Like currently, we've built NVMe systems for people, especially in the media industry, where they need really high throughput for doing like color correction, where we're talking like, we need to be able to pull 2 gigabytes per second to each color correction machine, and we have 5 of them in the office.
Yeah.
And so we need huge amounts of bandwidth, and ZFS is able to do that, no problem. When you get into the more IOPS heavy workloads, that's where ZFS is only getting 40 or 50% of the performance of the drives, because the drive spends some of its time idle, because ZFS isn't being able to throw work at it fast enough. And that's what we're looking at fixing. But when these drives can do 1 million IOPS each, getting only 40% of that is still a lot more IOPS than we had even just a year or two ago. And so it's not any reason to avoid using ZFS for sure.
Yeah.
There's a lot to be.
It absolutely works. You absolutely get the performance enhancement out of it. And what does the roadmap look? This is where kind of an open source discussion here. Everyone wants the feature, and everyone goes, "When are you guys going to do it?" And well, there's a process by which people have to get paid to do the actual work. Open source is a great development model, but there's at the end of the day, developers such as folks like you and all the people at Klara that have to do this. So, what's the roadmap kind of look like? That what are we thinking?
Yeah, there's part of it is that optimizing performance isn't usually as easy as just go do it.
Yeah,
Oftentimes
yeah,
it's what is the specific workload, and so that's why we're trying to find different people that have different specific requirements for performance. Whether that's if you're running a database and it's all really small blocks, or you're running VMs and it's kind of smallish but maybe a little bit bigger blocks, like 16 or 32K instead of 8K for a database. And then people doing things like media that are going to be really big chunks. And in order to get this right, we have to kind of have all of those use cases and be able to test them so that when we're making it better for one use case, we don't make it worse for the other use case.
yeah.
And the part of the goal of this is to make ZFS maybe not quite auto tuning, but out of the box, it works well for everyone, and that you can tweak it to be even better for you, but especially if it can do more of that without you having to twiddle a lot of knobs. Because the other thing we've learned from years of working on software is if you expose a lot of tunables to people, they will try
They
the
will tune
weirdest
them.
values,
And
and
they might
especially
even use
really weird
AI,
combinations.
and they might even use AI, which by the way, I'll link to the Claire article, which it made me laugh when you wrote that article of using AI to tune ZFS and what it gets wrong. It was just, it was great.
Yeah, well, the most recent one I saw was when it made up a setting that didn't exist. And it's like, yes, tuning that setting would be great if there was such a setting.
Yeah, that something
It's
doesn't
like
exist.
you hallucinated a setting.
How would ZFS identify the drives, the different types? I remember there's a little bit of discussion around this.
Yeah, that's part of the difficulty is, especially because there could be layers in between, right? Like if you have NVMe drives, but you're connecting them to a tri-mode controller, like a LSI HBA, then to the operating system, it might not look as the same kind of device. And it might not be clear that that is an NVMe, not an SSD, and not a hard drive. And then even if you have NVMe, right? If you're directly connected to PCIe, then sure, you will see NVMe in the device name and so on. But what if it's NVMe over Fabric? Then there's a TCP/IP connection between the host and some other chassis where the disk is, and each of those maybe is actually different in the latency aspects, right? Like if you're going over the network, you're going to maybe have additional latency that you wouldn't normally have on an NVMe that was directly connected to the PCIe bus of your CPU. And so a lot of work has to go into looking at kind of latency thresholds and so on, but you can get tricked by those, right? Even a hard drive can seem to respond really quickly if you happen to ask for something that's in the 256 megabytes of cache that the hard drive has on board. And so you can't use any one metric, right?
You
We
have to
can
be
look for
implicit at
NVMe
some
in the
point.
device name, but that might not be enough. And we could look at the time, but that we could get tricked. And there are just so many different aspects. And then, especially when you get things where like you're doing it inside a VM and the VM doesn't know where the actual hardware is, or your hypervisor can emulate an NVMe device, and then underneath it's actually backed by something not as fast. And there can be advantages to that. Like we have another article on Klara's website where even if you're just using hard drives or SSDs, if you have your hypervisor emulate NVMe for the guest, it allows the guest to send more commands down to the lower layer, which allows ZFS on the host to queue up more commands and decide how to do stuff and prefetch more and actually get more performance out of the same hardware.
There's a lot of layers here. I
Yeah, and then it
I
gets
think
even more complicated when NVMe devices are starting to do unique things and be a bit less pretending to just be a hard drive. Um, like we talked about that flash translation layer where it keeps the
yeah.
table of this logical block address actually is on this specific piece of NAND. As we start to see the 100 terabyte NVMe devices, they've realized that it takes a lot of DRAM on the hard drive or on the NVMe drive to keep track of that table because it has to be in RAM to be fast enough. So if we made the sector size bigger, instead of 4K sectors, if we did 16K sectors, we would need 4 times less DRAM, and that would make the drive less expensive. And when everything's competing on dollars per terabyte, that could be a big selling point. But then the file system has to deal with the fact that the sectors are actually 16K now. And we talked about the backwards compatibility. Most of them can still pretend or accept writes at a smaller level, and then the drive will do the read modify write internally. But if ZFS was aware of that, it could try to align things to 16K as best it can to avoid the drive having to do a bunch of extra work.
And that was interesting. And I think to extend this further, one of the things you mentioned was the drive manufacturers are going, hey, what if we can talk to ZFS too? And can ZFS help us out? Because once you get to these larger scales, I think that's where it gets even more challenging to the error correction on the drive and can it interface with software?
Yeah, especially if you're looking at the newer QLC or even PLC NAND, where they're storing more bits in the same cell. And so instead of, like SLC of just, it's a 1 or a 0, then, with the MLCs and TLCs, we got 3 bits. And then when we get more, that's that many unique charge levels where it can get a lot harder to tell if that is, supposed to be this charge level or that charge level when it drifts in between.
Yeah.
And so one of the manufacturers of the QLC drives was talking to us about, well, when our firmware decides that that sector is not as clear on whether that should be these specific 3 bytes or these specific 4 bytes or a different series of 4 bytes, what if we could ask ZFS to reconstruct from parity what the right value is and write it back to us so that we could reset the charge levels on that NAND cell and know we definitely have the right answer. And how do you have this kind of out of band communication between the hard drive and ZFS? Especially since the way ZFS works is it's this tree of block pointers. And so if you access a specific object, we know, okay, the first 128K of that object are in this part of the hard drive and the next are on that part of the hard drive. But there's no way to go the other way around. If you tell ZFS, hey, there's a problem in this sector number, it doesn't know which file that is. And it doesn't know what the checksum should be. It has to basically search the entire metadata of the pool until it finds an object that is on that sector, and then it will know, hey, here's the block pointer with the checksum and so on. And can we make some more efficient way than having to just search every file on the hard drive and see, are you in this sector? Are you in this sector? Are you in this sector? Until we find the right one to be able to regenerate.
Oh, that is a fun and interesting challenge. This is the stuff I like talking about because it's cool to say ZFS does this or that, but getting into the nuts and bolts of how it's developed and how it aligns to drives, I think is it's good deep thinking to understand why you can't just say it's faster or it doesn't work, because it is faster and it does work. But these little alignment things, or like you said, even changing it to a 16K sector size, could be great, but requires more deeper understanding to get the efficiency back out of it.
Exactly, because in general, the bigger sector size will generally be more performant because you'll get more megabytes or gigabytes per second out of the same number of IOPS because each IOP is bigger. But it also can cause problems with slack, right? If we actually tell ZFS don't ever, every sector is at least 16K, then if you write a 1K file, there's going to be some waste, right? ZFS has compression, but it can't compress something to less than 1 sector. So that means every file up to 16K is now doesn't benefit from compression unless we can do what ZFS calls an embedded block pointer, which is if it compresses to less than like 110 bytes, we can store it instead of the checksum in the block pointer. But that's only for like microscopic files. But if suddenly all these files that, if you have a bunch of 1 kilobyte metadata description files, for example, in certain media workloads, there's a little text file that describes each frame of a movie. And if each of those frames is like a 90 megabyte 8K video file, that's one frame, and there's a 1K text file with it. If you have millions of frames, you have millions of these 1K text files. And if they go from taking 4K to taking 16K of space, times millions or billions of files, they can end up using up a lot more space, even though it's the same number of files and the same actual amount of data. So how can ZFS both align to that 16K to be more efficient, but not use it as a sector size so that it can still write, 4 different 4K files in one 16K sector and let the hard drive do the read, modify, write magic, or ZFS can maybe do some of it itself even, but trying to get the right balance between, the blend hammer of just updating ZFS's sector size and, the trade-offs that have to do with that.
And I think one of the, and I think you guys actually had done this. Isn't there a metadata storage for each drive, like that, a tag that can be added to a drive, or maybe we could store some of that information? Or am I wrong
A
about
bit.
that?
So at the way ZFS works right now, there's a label. There's 2 copies at the beginning of the drive and 2 copies at the end of the drive. In the current version of ZFS, each of those is 256 kilobytes, half of which is the ring of Uber blocks that you use when you first import the pool, like when you first boot up, and it, every time you copy on write and do a transaction, or a transaction group, we write the next Uber block, and we basically just overwrite them in a ring, so that when you boot up, you try the newest one, but if it wasn't finished all the way because the power went out or whatever, then we just go back one and import that one. And that's how ZFS doesn't need a tool like FSCK and can instantly recover whenever, the power goes out in the middle of a write operation. But as we increase the sector size, that same 128K that holds the ring of Uber blocks, if each Uber block is 4K right now, we can only fit 32 versus the original 128 we could fit, because the Uber
Oh,
block is actually a kilobyte. And so it took 2 512 byte sectors. But now that the most drives are 4K, we only store 32 instead of 128. But if we go to 16K, then we only have 8 Uber blocks. And if
mm.
we save one off because we have a checkpoint, then we only have 7. And that gets to be a really short window to be able to recover from. And then if somebody has, a 32K sector drive, then they only have 4 or maybe 3, and that gets pretty out of hand. So at the ZFS Developer Summit last year, Klara proposed, and we now have a draft pull request out to change that label to actually be quite a bit bigger, like the first 512 megabytes of the drive, because most drives are plenty big. And actually,
Yeah.
ZFS will only use the larger label size if the drive is big enough, or if you force it to for like the test suite or whatever. So that, if you're creating a 10 gigabyte disk image for a VM, you might not want to lose 512 megabytes of that to the larger label size. And so it'll keep using the small labels for small disks. But with this bigger size, we can store more information, we get extra metadata, and we get the entire pool config. Whereas right now, because of the limited space, ZFS only stores the config, like each VDEV knows about its siblings, like the other disks that are part of that VDEV, and it knows how many other VDEVs there are, but it doesn't know anything else about any other VDEVs. So if
Okay.
you have 2 RAID Z2s, each label only contains information about its own RAID Z2. Whereas with the new larger label, the whole pool config can be written into the disk. And this can also speed up importing the disk because you don't have to read the label from every disk and figure out how many unique VDEVs there actually are.
And at the same time, couldn't you put some drive information in there as well about what type of drive it is?
Yeah. And in general, something that Klara did previously was adding the concept of VDEV properties. So you know how you have properties on a data set and you have properties on a pool. You can now also have properties on a disk where you can say, this disk has certain extra information. So there's both structural stuff in part of ZFS, but there's also user-defined properties. So on my disk, there's usually like the information on when the warranty for this drive expires, or here's the part number, or even the URL to order a replacement drive. That can be very helpful when the drive fails and you're like, which kind of drive was it? The drive doesn't work anymore. I can't see. And I don't want to have to go down to the data center and pull the drive out and magnifying glass the label to find out. It's like, oh, here's the replacement part URL right here.
That's great. Because then we could also define the types of drives, which then
Yep.
would align ZFS. Because as we alluded to earlier, it's hard to determine exactly based on performance what type of drive it is. It's not as obvious
Exactly. And
as
maybe
with all
if
the
you have a
layers in
setting that
between.
defaults to ZFS will try its best to detect, but you can say, I know this is a hard drive. I know this is an SSD. I know this is an NVMe. Or I know this is the new thing that hasn't been invented yet.
Oh, I wonder what that is now. That is, I thought by now, 20 years ago, we're moving from spinning rust to magical optical things I seen in Star Trek. And we haven't got there.
Linear chips.
Yeah, the linear chips. Like this is what watching Next Generation. This is where we're going. And we didn't go there. I'm a little
I think
disappointed.
IBM had something that they talked
Yeah.
about once, but it never really went anywhere.
Yeah.
But even at the 45 Drives conference, we also talked about CXL or Compute Express Link. And while CXL.io would probably still be NVMe on the other end, it might be different performance enough that you'd want that as a different device type. So saying this drives an NVMe, but it's in a different computer. And so you need to treat it slightly differently, or that that information can also be useful when you're deciding how to lay out your RAID. It's like, well, if I'm going to combine the drives from a bunch of separate computers into one pool, I need to make sure that losing any one computer isn't going to take out too many drives in one VDEV.
Yeah, Wendell talking about the CXL stuff, man. It's like, ooh, I think I need to get one of those cards. You load it up with DDR4, which many of us have that laying around. Now the DDR5 is a thing, and they're a card. And I believe the way Wendell described it was, it's a NUMA without a CPU. Just it can
Yeah,
show. It's got different operating modes, but I think Gigabyte made the cards. I'll try if I find a link, I'll drop it in the description. But conceptually, this was just really interesting.
yeah, and the concept of memory tiering has been around since the 30s or 40s. I forget when the von Neumann paper came
Yeah,
out, but it's always that there's always a tier of memory that is faster than what you have, but it's more expensive, and a tier that's slower than what you have, and it's less expensive. And so whether that's like, we have the L1 cache on for the CPU, and then the L2, and then the L3, and then we have RAM, and then we have maybe the NVMe, and then an SSD, and then a hard drive, and then a tape, and then the cloud or something.
yeah.
And each one of those maybe has a lower cost per gigabyte or terabyte or whatever, but it's also, you can't have as much of it.
Yeah. So, yeah, the complexities of it, but this is what makes it fun. And this is watching the innovation and watching it go forward. So it's all on the roadmap. There's a lot of awareness. It's going to require some sponsors to get this type of code implemented.
Yeah,
But
so
it's coming.
especially if you have a use case where NVMe would be good, or you're already trying to use NVMe on ZFS, and you're only getting 50% of the performance you would like, we'd definitely like to hear from you and look at how we can tune ZFS and add features to ZFS to take maximum advantage of that.
Yeah.
One of the ones that came out recently, most of that work done by I think it was one of the government labs, Los Alamos and Lawrence Livermore, I think specifically, uh, added the option for ODirect. So basically, at the application level, you can say when you're reading or writing data, I know I don't need this again. And so ZFS can skip putting it in its cache and write directly to the NVMe or read it directly from the NVMe and skip the caching layer, which, when you're doing tens of gigabytes a second, can be helpful just in general to reduce the amount of processing. But also it means what you have stored in your cache doesn't get evicted to make room for some new data that the application knows for sure it doesn't actually want to read again.
Oh, that's
And so
interesting.
having the application be able to give more hints about, I expect to need this data again, or I don't expect to need this data again. Or even saying, I'm going to want that data in a few minutes. If you wouldn't mind loading it in the background for me, that'd be great.
Wow, that's like way more advanced adaptive arc. Like,
Yes, exactly. Instead of trying to just adapt, what if the application could tell you for sure, yes, no, or soon?
yeah. But that's a really interesting concept. I did not know that was a feature now.
Yep.
That is really cool.
Yeah. So
I,
if you have an application that could take advantage of that and need help with that, then definitely we'd love to hear from people that are looking to do that kind of work, because we've got a good start to it. One of the other things about the way ZFS worked in the past, when we sent IO off to the drive to get done, when it was completed in that interrupt handler that says, oh, all right, that data is completed, and we can send it back to the application now, that's when ZFS would then look at the queue of commands and pull the next ones off and send them to the hard drive. But it turns out, in hard drives where we had a single queue and the hard drive can only do one command at a time. It meant that you might have up to 32 commands queued to the drive, but when it completed one, it would tell us, and we could add one more to the end of the queue, and then it would be fine. But with NVMe, we can have up to like 63 queues, each which holds 64 commands. If we wait until it tells us that one of those commands is done before we add another command to the queue, that queue is probably going to be almost empty by the time we add one more command to it, and we're always going to be running behind. So what if ZFS could basically have a dedicated thread that was just pushing IO down to those queues and keeping them full, and then when the interrupts come in and say it's done, we just have to tell the application. And this way we can keep that queue more full and avoid the problem where the CPU can't sleep for a small enough time to not sleep through the next 3 notifications that another IO is complete from the NVMe, because the latency is so low and the NVMe, rips through those commands really, really fast.
That's interesting. I think what's also fascinating, you brought up a couple of times, is that the movie industry is a big driver of a lot of this. Anytime you work with these absolutely incredibly big files, the camera systems have exponentially gotten to where they shoot things at such a high resolution. They outpaced, I think, some of the storage ability to handle it all easily. So that's where some of that cutting edge is coming from. They're like, we're just going to make a bigger sensor and these cool cameras and shoot it all in RAW. And they're like, well, where do we put all that though?
Well, in particular, it's like we need to keep all the raw footage from all the takes until we're done editing the movie, because we might go back and need some of that. Or
Yeah.
even when we're done editing the movie for the trailer, they might want some other bit or whatever. It's like we have to keep a lot of this for a long time. And so we need a way to do that that's not going to break the bank, right? We need storage that is the lowest cost per terabyte that we can get. And that's one of the areas ZFS excels at, because on top of being able to get the most out of hard drives, especially with a streaming workload like this kind of media archiving is, but just the fact that there's no license for the software, right? It's open source software you can just use, means it can be the best solution to that. And oftentimes means it's the only solution where you can actually afford to have 2 of them so that you can have a backup.
Yes, exactly that. It's some of the big giant boxes I've installed that I've showed pictures of. Let's just say the big superhero movies you've probably viewed are probably living on ZFS somewhere.
Yeah.
Being edited or something. It's Hollywood runs on ZFS more so. I drive me crazy. People, it's not really open source, isn't using the enterprise. I'm like, do you ever watch a Hollywood movie? Let's just say it's all stored on ZFS. It's probably the most popular place to find it.
Yeah. Or like, have you heard of Lawrence Livermore National Labs? The
Oh
people
yeah,
that are doing the actual fusion stuff and have the
yeah.
power thing that actually is running for where do you think all the data for that lives? They
They're
have pictures of their like 40,000 hard drives running ZFS.
CERN. Am I correct? In CERN uses it as well. I remember they had an
Um,
article about they had built one of the largest ZFS things a few years ago, and I imagine it's
yeah, I think,
bigger now.
and then yeah, but there's a lot of the giant supercomputers because it's the only file system that can actually try to address that much storage at once.
Yeah, at a performant level. I mean, there are other file
Exactly.
systems, but yeah, there's
Well, even there, like a lot of times, what those labs are doing is using Lustre, the distributed file system, on top of a whole bunch of separate ZFS machines.
yeah,
But it's because they need the data to be resilient against loss of a node or a hard drive.
yeah,
And so getting those 2 things together really makes a solid system that they can also understand and manage.
yeah. That's a big factor of it too. So being able to actually manage it. Well, I think we've covered this topic. Is there anything more we have to add to the NVMe? Do we have it all now? Other than it
Well, there's
doesn't,
lots more
it's
to go, but
there's
yeah.
well, we could probably talk forever about it. I think we covered the key points here. So we got a few more points we got to go, or we got them all.
No, I think that's pretty much it. Yeah, if you're interested in using NVMe for a specific workload or are already using NVMe and ZFS together and want to get more out of it, we'd definitely love to hear from you. And yeah, there's lots more of interesting stuff coming as
Yeah.
we continue to make all these improvements to help ZFS catch up to the hardware.
ZFS is absolutely under heavily active development. We gotta
Yes,
keep those particle data stored somewhere in Hollywood movies as well.
exactly.
All right. Well, thank you very much, Alan. This was great. Appreciate having you here.
Yes, thanks for having me.
All right.
Talk to you soon.